Okay, so today we're going to discuss about the first order systems. This is in line with the other system models. So over here, we are going to discuss about the first order system. So consider a first order system uh, with yt as the input to the system and xt as the output that you can see in the equation over here, and which has a forcing input b naught y and can be described by a differential equation of the form a1 dx by dt plus a naught x is equal to b naught y, where a1, a naught and b naught are the constants. So this is the equation, this is the system that we will be discussing today. So over here, when we are going to study this first order system as well as the second order system, we will be dividing our concern towards natural response and the forced response. So we'll be applying both the conditions to both the systems, that is for the first order system as well as for the second order system. So likewise, over here it has been taken as the yt is taken as the input. Suppose we are considering a situation when the input is 0. So when the input is 0, the system is having no forcing signal acting on the system. So that means system will work according to its natural response without the application of any external force. For that particular system, if I see this equation a1 dx by dt plus a naught x is equal to b naught y, over here if you see, if I'm not considering the input, then the right hand side is going to be 0. So we will be left with a1 dx by dt plus a naught x is equal to 0. Now rearranging this, we can write it like this: dx by x is equal to minus a naught by a1 into dt. So integrating this between the initial value of x is equal to 1 at t is equal to 0, that is a unit step input, and x is at t gives. So that means natural x, I'm taking just integration of this above equation. So we got natural x, natural logarithmic x is equal to minus a naught by a1 into t. So further, just taking anti-log of that, what we'll be getting, x is equal to e raised to power minus a naught into t by a1. So this is a kind of a natural response that we are getting. We could, however, have recognized that the differential equation would have a solution of the form x is equal to a e raised to power st. This is a natural solution for a first order system. So you must have studied that, where a and s are constants. We then have dx by dt is equal to, just taking the differentiation of this, x is equal to a e raised to power st, just taking its differentiation, what will be getting? Dx by dt is equal to s a e raised to power st. And so when these values are substituted in the differential equation, what will be getting? a1s a e raised to power st plus a naught a e raised to power st is going to be 0. And so a1s plus a naught is equal to 0. Lamba, you want to ask something? You can. Hello. Okay. So a1s plus a naught is equal to 0, and therefore s, the value of s would be in that case is equal to minus a naught by a1. So previously we got that solution, this one in the previous page. X is equal to e raised to power minus a naught t by a1, and over here it is coming out to be x is equal to a e raised to power minus a naught t by a1. So this is known as the natural response. Since there is no forcing function, we can determine the value of the constant a given some initial condition. Thus, if x is equal to 1, then t is equal to 0, then a would be equal to 1. So in this equation, in this particular equation, you can see that x is equal to a e raised to power minus a naught t by a1. So over here, if I'm considering x is equal to 1 at t is equal to 0, then if I'm putting all those values, then what I'm getting is a is equal to 1, which is the previous solution on the last page that I have derived. So x is equal to e raised to power a naught t by a1. Okay. So this is the graphical representation of the solution. So according to this is exponential and decreasing exponential function. So with the time, the value of x is decreasing. So you have given some input to system and you are getting some output xt. Now we are getting how to remove this. Okay. Now consider the differential equation when there is a forcing function. So I already told you we will be considering the system acting in two ways, one with the natural response and one with the forced response. So here what I'm getting is a1 dx by dt plus a naught x is equal to b naught y. This is the same equation that I'm taking from the last page. The only thing is that in the previous case we have considered y equal to 0, but over here because we are considering it as a forcing input, so therefore consider the solution to this equation to be made up of two parts. That is x is equal to u plus v. One part represents the transient part of the solution and the other the steady part. Okay. So because you can see that over here, this is a transient part because this depends upon t, and this is your steady state solution. Okay. So these are the two things which you can have. Okay. So now consider the solution to this equation to be made up of two parts. We can consider x is equal to u plus v. So while I'm considering x is equal to u plus v, one part represents the transient part and the other part is a steady part that I already told you. So replacing the x with the u plus v, what I'm getting is a1 d in brackets u plus v upon dt plus a naught into u plus v is equal to b naught y. Now rearranging this equation, what I'm getting is just rearranging the things, and you can see over the screen. So what will be getting a1 du by dt plus a naught u plus a1 d1 dv by dt plus a naught b is equal to b naught y. If we let this equation, okay, if we consider this equation as my total forcing equation, then this equation must be my natural response. And already for natural response, we have already got the solution in the previous equation. So just keep your mics shut off. And so two differential equations, one of which contains a forcing function and one which is just the natural response equation. This last equation is just the natural equation which we solved earlier in this section, and so has a solution of the form of this. So u is equal to ae raised to power minus a naught t by a1. The other differential equation contains the forcing function y. This is the natural response. Okay. This is the natural response. Already in the previous, we have done this. The other differential equation contains the forcing function y. For this differential equation, the form of solution we try depends on the form of the input signal y. Okay. For a step input, when y is constant for all times greater than 0, that is y is equal to k, we can try a solution v is equal to a. Right. This is a constant thing where a is a constant. If we have an input signal of the form y is equal to a plus bt plus ct square, where a, b, and c are the constant, which can be 0 also, then we can try a solution which is of the form v is equal to a plus bt plus ct square. For a sinusoidal signal, we can try a solution of the form. But if there is a sine kind of a problem we have, then v is equal to a cos omega t plus b sine omega t. To illustrate this, assume there is a step input at time t is equal to 0. We got a step input. Meaning of step input is that when time is 0, you got a response, you got a forcing response as something equal to value of a. So v is equal to a in that case, this one. Okay. So if I differentiate the previous equation, this one, the last equation, this one, this, okay. If we differentiate this, and if I use the constant value v is equal to a, then differentiation of a constant will give you 0. So thus, and if I'm going to differentiate this dv by dt, because v is a constant, so if I'm taking a differentiation of that, please switch off your mic, please. Somebody is Mr. Krishan. Okay. So if we let a1 dv by dt plus a naught v is equal to b naught y, And over here dv by dt, because there's a differentiation of a constant, so this term will going to be 0. So what you are left with, a naught v is equal to b naught y. Okay, so using that, a naught v is equal to b naught y, this one. So because v is equal to a, we have considered y is equal to step input, we have considered as equal to k. So this v is equal to b naught by a naught into k. So this is the solution for the forcing function. So the total form of the solution would be u plus v, and so therefore x is equal to a e raised to a minus a naught t by a1 plus b naught by a naught into k. We can determine the value of the constant a given some initial condition. Thus, if the output x is equal to 0 when t is equal to 0, right? So we are trying to find out now the value of a with some initial conditions. So if x is equal to 0, then when t is equal to 0, then x is equal to 0 means over here. So if I'm going to put t is equal to 0, so this e raised to power 0 is 1. So I'm left with this equation: 0 is equal to a plus b naught by a naught into k. Thus a is equal to minus b naught by a naught into k. This is the value of a that I'm getting over here. I'm going to put that value of a over here in this previous equation. And this is the kind of response that I'm getting if I have the two functions. One is a natural function, that is a natural response. Another one is a forcing function. So when t goes to infinity, the exponential terms tends to 0. The exponential term thus gives that part of the response which is a transient solution. The steady state response of the value of x when t goes to infinity, so b naught by a naught k. Thus the equation can be written as this: x is equal to steady state value into 1 minus e raised to power minus a naught t by a. So this is the kind of solution that you get over here. Now there are you can take some examples of first order system. The one is, as it is further illustration of the above, consider the following example for a first order system. An electrical transducer system consisting of resistance in series with a capacitor, and when subject to a step input of size V, gives an output of a potential difference across the capacitor V, which is given by the differential equation. So RC dV by dt plus V is equal to V. Okay. So you got the input, there is a step input. This is how the exponential is behaving. This is according to the previous results. So by putting all the values in the previous solution that we have just got, this is kind of the solution we are getting for this particular electrical problem. So V is equal to V minus e raised to power t by RC. Now further, consider an electric circuit consisting of a 1 mega ohm resistance in series with a 2 microfarad capacitor. At a time t is equal to 0, the circuit is subject to a ramp voltage of 40 V. That is, the voltage increases at the rate of 4 V every 1 second. The differential equation will be of a similar form, so that given the previous example, but with a step voltage V of that particular example replaced by a ramp voltage 40. In the previous example, we have got a constant kind of a voltage, but over here our voltage is also varying. So instead of using a constant voltage V, we have got a varying voltage which is a 40. So just replacing that value of V over here, what we get is RC dV by dt plus V is equal to 40. Already we have got the values for resistance and the capacitor. So by putting all those values over here, what I'm getting is 2 dV by dt plus V is equal to 40. Taking V is equal to Vn plus Vf. What is Vn? Is the natural response. Vf is what? Your forcing response. We have over here as two, like in the previous problem we have done, we have got one natural response and we have got one forcing response. So these are the two responses that I've got. For the natural response differential equation, we can try a solution of the form Bn is equal to a e raised to power st. So this was the natural response. So we have used this as a response over here in this equation. Hence, using this value, what we are getting is 2a s e raised to st plus a e raised to st is equal to 0. So thus s is equal to minus half, and so you can use all those mathematical things over here and you can get some final equation. So this is kind of the response you will be getting. So this is just a application of the first order differential equation system. Now next is a second order. So in your syllabus, the next mentioned is a second order system. So many second order systems can be considered to be analogous to especially just a stretched spring with a mass and some means of providing damping. So we got a spring, we got a dashboard system over here. Then we have got a mass and we have applied some force over here. So in the previous lectures, I have told you that the equation describing the relationship between the input of force F and the output of a displacement x, this is equal to m d2x by dt plus c dx by dt plus kx is equal to F. So the way in which the resulting displacement x will vary with time will depend upon the amount of damping in the system. Thus, if the force was applied as a step input and there was no damping at all, then the mass would freely oscillate on the spring. So this is kind of a, this example is nothing but a kind of a mechanical vibration problem. So in mechanical vibration, we do these kind of a second order differential equation problems. So over here, this is your, you can say inertia factor, this is your dashport system factor, and this is equal to your spring factor. So all those three things are to be considered for a differential equation for the second order differential equation for the mechanical vibration, and F is equal to the force which has been applied on the system. So now natural response, I'm considering a natural response. If I'm considering natural response, then obviously the right hand side, the where the force has been applied, that is going to be 0. Now consider a mass on the end of a spring in the absence of any damping and left to oscillate freely without being forced. The output of the second order system is a continuous oscillation. Now suppose we describe this oscillation by the equation x is equal to a sine omega n t, where x is the displacement at a time t, a is the amplitude of oscillation, and omega n is the natural angular frequency of the free undamped oscillation. Differentiating this, what we are getting is x is equal to a sine omega n t, differentiating is dx by dt is equal to omega n a cos omega n t. Similarly, the second order differential equation, second order of this differentiation would be minus omega n square a sine omega n t. Now what is a sine omega n t? It is x. So that means we can represent this the second order of differential of x is equal to minus omega n square x. Now d2x by dt2 plus omega n 2x is equal to 0. But for mass m on a spring stiffness k, we have a restoring force of kx. So m d2x by dt is equal to minus kx. This can be written as d2x by dt2 plus k by m into x is equal to 0. Okay, because we are considering a spring system only. We are not considering any forcing acting on the system. So from here, you can easily say that by comparing these two equations, omega n square is equal to nothing but equal to k by m, and x is equal to a sine omega n t. So from here, natural frequency of the system can be found out. Now consider when we have a damping also available. So now earlier we were considering only spring force. Now we are considering a damping force as well as. To solve this equation, we can try out the solution xn is equal to a e raised to power st, which is a natural response for a system as discussed in the previous example. So this gives dx by dt this and double derivative of this. So by replacing all these values in this particular equation, what I'm getting is ma s square e s to raised to power st plus ca this plus this. So from here, what I'm getting is ms2 plus cs plus k is equal to 0. Okay. So because a e raised to power st can be taken out common, and that is equal to 0. Thus xn is equal to a e raised to power st can only be a solution provided the above equation equals to 0. This equation is called the auxiliary equation. And from here, you can also find out the roots of the value of s. So this is a quadratic equation, ms square plus cs plus k is equal to 0. So from here, what I'm getting is a quadratic equation. So the roots of the s will be minus c plus minus underscore c square minus 4mk by 2m. And from here, what I'm getting s is equal to minus c by 2m plus minus under root k by m, c square by 4mk minus k by m. But omega n square by k, omega n square is nothing but equal to k by m. So by replacing this k by m equal to omega n square and just putting all other values like zeta square is equal to c square by 4mk, we get this final equation. S is equal to minus zeta omega n plus minus omega n under root of zeta square minus 1. What is zeta? Zeta is known as the damping factor. Okay. So now depending upon the zeta, which is a damping factor, we divide our response, that is a mechanical vibration response, into three kinds. One is overdamped, one is underdamped, one is your critically damped. So if zeta, the value of zeta is greater than 1, there are two differential equation real roots are s1 is equal to minus zeta n omega n plus omega n under root of zeta square minus 1. Similarly, s2 is equal to minus zeta omega n minus omega n under root of zeta square minus 1. So these are the two roots. So the general equation will become xn is equal to a e raised to power s1t plus b e raised to power s2t. This is the overdamped solution. Then we have a critically damped. when zeta is equal to 1. When zeta is equal to 1, then in that case, S1 and S2, both roots of the equation will be equal to minus omega n. And for that, our solution will become from the previous solution. You can compare that in your free time. So xn is equal to at plus b e raised to power minus omega n t. Okay, this is what you are getting as a response in a critical dam. Similarly, what we are getting for underdam. In underdam, what is we having? Zeta is less than 1. So when zeta is less than 1 in under root, you will be getting something response as minus 1. Negative value is coming out in square root. So taking out this negative value as minus 1 under root, and this is nothing but known as iota. You must have studied that, into 1 minus zeta square. So what I'm getting is S is equal to minus zeta omega n plus minus zeta iota omega n under root of 1 minus zeta square. Okay. So if we let, just hold on. Still you are able to see this screen, right? So if we let omega is equal to omega n under root of 1 minus zeta square, then we can write S is equal to minus zeta omega d plus minus iota omega. And so the two roots will be minus zeta omega d plus iota omega, and S2 is equal to minus zeta omega d minus iota omega. So these are the two roots that we are getting from the underdam system. And accordingly, these are the two equations which will be coming out from the response for the underdam system. If you want to study further for this particular like critical dam, overdam and underdam, then there is a very good book available that is by G.K. Grover. That is a book for mechanical vibration. So this system has been explained very well in that particular book for a mechanical vibration. This topic is entirely of mechanical vibration. Then in the next, this was a natural response. Now we are moving towards a response with a forcing input. When we have a forcing input f, the differential equation becomes m d2x by dt plus c dx by dt plus kx is equal to f. This is a forcing. So by replacing we for a system which has the natural response as well as a forcing response, so md2, that is xn plus fx by dt2 plus c this. So what we have done, we have replaced x with the natural response plus forcing in response. So if we let md2 xn by dt2 plus c dx by dt plus kx n is equal to 0, this is our natural response, this one. Okay, so we have segregated out like natural response separately with the force. Already we have dealt with the natural response, this one, in the previous, just in the completed article, how to deal with the natural response when the force is 0. So you have found out the various responses for overdam system, critical dam system, underdam system. That was a natural response. Now this gives you the forced response. Now what we have got is md2 x by dt2 plus c dx by dt plus x kx is equal to f. Now on the right hand side, what you are getting is a forced equation. So that means this is kind of a system you can think of like, suppose you have compressed the spring earlier and then you left it out and it vibrates on its own. So that is kind of a natural response. So in a forced response, what is happening? You are continuously applying a force on the spring. So you're continuously pressing the spring and then releasing it, then pressing again, then releasing it. So system is not able to vibrate on its own. So system is vibrating under the impact of the external force. So that is a kind of a forced response that you are getting from this. So when system is allowed to vibrate on its own, then the system vibrate with the natural frequency, right? But in this case, when the system is under the external force, then the system vibrates with the forced frequency. So that will not be the natural frequency of the system. So now already we have dealt with the natural response. So over here we'll be discussing the forced response in a second order differential system. Okay, so md2 x by dt2 plus c dx by dt plus kx is equal to f. This is what you are getting. Again, we can try some solutions like xf is equal to a, which we have done for the first order system. This is already done. Then dx by dt is equal to 0, and differential second will also be 0 because this is a constant. Thus, when these are substituted in the differential equation, what we are getting is 0 plus ka is equal to f. So a is equal to what? F by k. Okay, because a is equal to x, so that means xf is equal to f by k. So what we have done is we are replacing this. So in the overdam system, what was our natural response? This was our natural response, this one. Okay, so already you have done this. This was the natural response. Only thing that we are adding over here as a forced response is f by k. Okay. So x is equal to a e raised to power s1t plus b e raised to power s2t plus f by k for the critically damped system. And similarly, what was the solution for this? So this was the solution for critically damped, and what we have added is forced response over here. Okay. Similarly, what was this? This is the under damped system response, and what we have added is a forced response into this. So this is a complete solution for the forced system. Okay, so these are the things. Then we have some examples of second order differential equation. So we consider a electrical analogous system over here. Consider a series RLC circuit. So you can see RLC circuit have been put in series with R is equal to 100 ohm, L is equal to 2 Henry, and C is equal to 20 microfarad. When there is a step input V, which has been applied over here, the current I in the circuit is given by d2I by dt2 plus R by L di by dt plus 1 by LC into I is equal to V by LC. Okay. If you compare the equations with the general second order differential equation, right? This was the equation that you were getting in the forced. Then the natural frequency, you can find it out from here. From this, you have compared this solution already have been discussed in the system models in the previous lectures. And this is how this equation have been placed for the second order differential equation. Just by comparing the two equations, what you are getting is omega n is equal to omega n square is equal to 1 by LC, which you all already know from your 10+2 class, that this is how the natural frequency is being calculated for an inductor and capacitor system. So omega n is equal to 1 by under root LC, where omega n is the natural frequency, which is 158 Hertz. Similarly, comparing with the general second order equation, what we have got is zeta square is R by L square. So again, we are comparing the values with the to get the damping factor. So this is a value of damping factor that you are getting 0.16 because zeta is less than 1, so system is under damped. So actually we are most interested in under damped systems, because when the system is over damped, the system's response is sluggish. Once it goes for the vibration, then it's not able to come back to its original position because it's over damped. When the system is critically damped, which is a very dangerous situation for the system, because in that case, the system, the external force and system's natural frequency both matches with each other, which is kind of a resonance, we call it as. And because of that, there is a huge damage to the system. So mostly we try to avoid those situations, and we only work in under damped system, which is coming out this case as well, like zeta is equal to 0.16. And since zeta is less than 1, the system is under damped. The damped oscillation will be omega is equal to omega n under root 1 minus zeta square. So omega is equal to 156 Hertz. See, right? And for the under damped system, because now it is clear that the system is under damped, so that means definitely what we are going to do, we are going to choose the equation for response for the under damped system, which is already we know this is the equation. And now we know all those values, we are replacing those values, we are putting over here. And so finally, what we are getting is this is kind of a differential equation solution that we have got from this. Now consider the system. Now consider the system shown in figure 19.11 over here. Okay, so earlier we have discussed the electrical system. Now there is a torsional system. Already this system has been discussed with you in a previous class. So net torque is equal to what? T minus C. This is the means kind of a damping system. Then there is a torsional spring system. So T minus this values, but we get the net torque. So the net torque is equal to this value already has been derived. And then what we are going to do is, this is the final equation for the torsional system. We are comparing this equation with the equation with the which we have found out. And accordingly, this is what we are getting is zeta square is equal to C square by 4 IK. Okay. So, all right. And we'll discuss the Laplace transforms in the next class. With that, I'm closing this class. Okay, so you can ask me your questions now, please.